We're on problem 106. 106. The present ratio of students to teachers at a certain school is 30 to 1. So the ratio of students to teachers is equal to 30 to 1. If the student enrollment were to increase by 50 students and the number of teachers were to increase by 5, the ratio of students to teachers would then be 25 to 1. So if we increase the students by, what do they say, by 50 students, and increase the teachers by 5, so teachers plus 5, the new ratio is going to be 25 to 1. 25 to 1. What is the present number of teachers? So let's just simplify these a little bit. We could cross multiply. Well, we could just write S over T is 30 over 1 is just 30, is equal to 30. Or S is equal to 30T. And let's substitute that into this equation, because we're going to have to solve for the present number of teachers, which is just T. Excuse me. So let's substitute this here. So we get 30T plus 50 over T plus 5 is equal to, well, 25 over 1. That's just 25. And then, let's see what we could do. Let's multiply both sides of this equation by T plus 5, and you get 30T plus 50 is equal to 25T plus, what's 25 times 5? 125. 125. I could probably, well, I won't worry about that. Let's subtract 25T from both sides. You get 5T plus 50 is equal to 125. Subtract 50 from both sides. You get 5T is equal to 75. And then T is equal to, let's see, 5, is it 15? Right, it's 15. T is equal to 15. 15 times 5 is 50 plus 25, right, 75. T is 15, so the answer is E. Next question. Don't want to run out of space, I'll just do it right here. Problem 107. 107. What is the smallest integer, n, for which 25 to the n is greater than 5 to the 12th? Whenever you see some type of an equation or an inequality where the variables are in the exponent and you're comparing numbers of different bases, your first thing that should register in your brain is, how can I get these to be in the same base? And it should be pretty obvious here, because 25 is the same thing as 5 squared. So let's rewrite it that way. This statement is equivalent to saying 5 squared to the n is greater than 5 to the 12th. And 5 squared to the n, that same thing as 5 to the 2n, is greater than 5 to the 12th. And this right here is going to be true. This is going to be true when 2n is greater than 12, right? When the exponent up here is greater than the exponent up here. That's when it's going to be true. You divide both sides by 2, and you get n is greater than 6. And that's, so what is the smallest integer n for which 25 to the n is greater than 5 to the 12th? So n has to be greater than 6. So we can't pick choice A, which is 6. Because if we pick 6, then we would have 5 to the 12th here, right? And then it would be an equality, but this is greater than. So the smallest integer, n, now has to be greater than 6. So n has to be 7. So that's choice B. Don't get tricked there. When you get 6 as your answer, you might want to pick A, but n has to be greater than 6. So it's essentially the smallest integer greater than 6 is 7. Problem 108. If x and y are different prime numbers, each greater than 2, which of the following must be true? Each greater than 2, they're both prime numbers. So, statement number 1, x plus y cannot equal 90, cannot equal 91. Let me think about that. If x and y are different prime numbers, each greater than 2, which of the following must be true? X plus y cannot equal 91. Let me think about that a little bit. That means that I can't have two prime numbers that when I add them together, equal 91. Well, let's think about it for something. They're greater than 2, right? They're greater than 2 and then they're prime. So what do we know about all prime numbers greater than 2? Well, we know that they're both odd, right? Well, all prime numbers are odd, as long as 2 is the only even prime number. So both of these have to be odd. So if I add an odd plus an odd, what do I get? Well, one way to think about it, this might be second nature to you at this point, but an odd number can be written in the form 2 times some integer plus 1, right? It's some even integer, some even number plus 1. So I could write the first odd number like that. Maybe I'll say this is x, right? And this doesn't, I'm just saying that x is odd. I'm not saying that x is prime. But if you're larger than 2 and you're prime, you're going to be odd. Otherwise, you're divisible by 2. And let's say y is equal to, I don't know, 2 times some other integer plus 1. So if you add 2 odd numbers together, you get 2 times k plus m, right? 2 times k plus m plus 2, which is an even number. When you add 2 odd numbers, you get an even number, right? So the fact that, so if you add 2 prime numbers greater than 2, you're essentially adding 2 odd numbers greater than 2. So they have to be equal to an even number. So they can't be equal to 91. So statement 1 must be true. Statement 2, let's think about it. Statement 2 tells us x minus y is even. So once again, x and y are definitely going to be odd numbers. When you add them, you get an even number. What happens when you subtract them? If I were to subtract y from x, what would I get here? If I were to subtract it, I would get 2 times k minus m, 2 times k minus m, and then the 1 minus 1. But this k minus m is going to still be an integer, right? These are 2 integers, so this is still going to be an integer. And they're different prime numbers, so k and m are going to be different, so this isn't going to be equal to 0. So the difference has got to be an even integer. An even integer. Now, it might be a negative even integer, right? Because we don't know that x is necessarily larger than y, but we know that it has to be an even integer. Even integer. So statement 2 is also correct. Now statement 3. Statement 3. X divided by y is not an integer. Well, we know that x is prime, right? We know that x is prime, which means it only has 2 factors, 1 and itself, and we know that x isn't 2. We know that y is another prime number. Now, if this statement right here, if x divided by y, if that were an integer, then that means that y divides evenly into x, which would mean that y is a factor of x, which would mean that x has a factor other than 1 and itself, which would mean that x is not prime. But they tell us that x is a prime number, and y isn't just the number 1, right? They're both prime numbers, and they are each greater than 2, so y is definitely not 1. So in order for this to be an integer, x would not have, in order for this to be an integer, x could not be prime. Since x is prime, and y is some number greater than 2, we know that this is not an integer. So all 3 of these statements have to be true, and that's statement E. No, excuse me. That's statement E. Problem answer E. Problem 109. Let me do a different color. 109. All of the following have the same value except. Okay, so we're just going to try to do the math real fast here. 1 plus 2 plus 3 plus 4 plus 5. All of that over 3. What's this? 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. Divided by 3, this is equal to 5. B. 1/3 times 1 plus 1 plus 1 plus 1 plus 1. Well, that's 1/3 times, this is 5, so this is equal to 5/3. So after we see the next answer, we should know where we're going. So the next answer, we have 1/3 plus itself 5 times, right? 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3. Well, that's 5 1/3, so that's also equal to 5/3. So we should immediately be able to recognize that this is different than the other 2. And assuming that there's only one answer, right? They say all of the following have the same value except. I think we've done enough math because we know that B and C are the same value. So, and A is already different. So A is probably going to be our choice. And if we kept going, D and E are going to have the same value. And just eyeballing it, it does look like that's the case, right? Yeah, it definitely looks like that's the case because if you look at the other two problems, yeah, you still get 5/3. And E looks confusing, but the fact that A is already different than B and C tells you that A is the answer. And I'll see you in the next video.